Greetings, users of internet, and welcome back to the Minecraft lab. This is lab number 2, Redstone Logic Gates. I'm all ready to go. I still got my lab coat and my goggles, and as you can still see, there is snow all over my lab from last time. I forgot to turn weather off, but that is now turned off, and we shouldn't have it snowing again, but I don't really feel like clearing all this snow. So, we're just going to have to deal with it as we move forward. This is lab number 2. This is the Logic Gates lab. And if you haven't seen lab number 1, the properties of Redstone's lab, please go back and watch that, because I'll be referencing a lot of the things I talked about in that lab. I'll be referencing them in this lab. Something to keep in mind is I'm going to be using different terms to address the same thing. I'll be using both logic gate terms and redstone terms, because logic gates inherently are not a Minecraft thing. Logic gates are a binary logic thing. Hence the term logic gates. They are used to describe the behavior of basic binary logic. The two different kinds, the reason it's binary logic is there are two different inputs and two different outputs. There are two different states of any given object in this binary system. There is on or off. I will also refer to this as yes or no, or powered and unpowered. They all mean the same thing. Yes, powered, and on are all the same thing. Off, powered, and no are all the same thing. And I'll be addressing them slightly differently as I'm talking about a redstone thing versus a logic gate thing. Logic gates operate on, if I put in a certain kind of input, what kind of output do I get? And we can use these basic logic gates and manipulate the way the input has to be given in order to get whatever output we're looking for. This should be in the default. The default state for this lab is all the inputs are going to be levers. The default or off state for everything, it doesn't matter whether you see pistons up or down. This is the off state for all of these logic gates. The default is off, and that default is all the levers are up. And as we go around, I'll start manipulating the levers, and we'll explore how the gates behave. But the default will always be up is off, and you will see that there is no power to these redstone behind the levers while they're in the off state. Logic gates operate once again on the principle that if I put in a certain input, what output do I get? If I put in a yes input on a certain gate, what kind of output does it give me? These basic logic gates were the way that original computers were built, which is why they were the size of rooms, because you had to actually wire these gates the same way we do in Minecraft. Of course, they weren't dealing with 1 meter by meter blocks. They could make them, centimeters or inches or whatever, or as small as they could, reasonably manufacture at the time. But they did have to, by hand, wire all of these very large gates, and all of the programming had to operate on, when I put an input that equals a yes for something, how does the output behave? How do I want the output to behave? That being said, we're going to talk about in each of these gates, when I put in a certain input, what kind of output do I get? And more importantly, why does that happen? Most other people's redstone tutorials will give you, this is an AND gate, and this is what it does. And they don't tell you why it works or how you might use such a thing. And that is why most people are completely lost on redstone, is anybody who actually knows what they're doing doesn't care enough to enlighten the rest of you, or enlighten the rest of us, as it was at some point. I learned eventually. But we, the knowledgeable, don't spend enough time enlightening you, the non-knowledgeable, to why it is this actually works. You can't apply these unless you know why they work and how they work. So that's what we're going to do today. We're going to start off very simply with the most basic logic gate, which is just an input-output gate, or really just a switch. This is very basic redstone. Hopefully you've seen this before. As I apply power, I apply a yes input, I'll get a yes output. Yes or on or powered, all the same thing once again. So I power the lever and it powers the piston. This is a yes leading to a yes. It's just a lever and a line of wiring, and it's very simple. Hopefully that shouldn't be too difficult to understand. The next one we mentioned in the last video, this is called an inverter. This does exactly the opposite of the input-output gate, or just the gate, so to speak. Each of these, we're going to do a bunch of different gates, and each of these gates has an opposite. I'll address them as we get to them. And the opposite these gates are the opposite in the sense that it does the opposite effect. Applying the same input on a input-output gate versus an inverter will have the opposite effect. Applying a yes input gives me a yes output on a input-output gate. On an inverter, applying a yes input gives me a no output. And the reason it does that is because of the torch that we talked about in the last lab, where as you apply power to the back of the torch, it will turn the torch off, and that torch is no longer emitting power, so this will not be power. So as we apply, or as we remove the power, that torch can turn back on, and that will extend once again. Resetting these both to the default state, we're getting a yes output here with a no input. That's the way inverters work. And as we go down the line, it's important to keep in mind that the input does not necessarily have to be a lever. As I addressed in the previous video once again, we have levers, we have buttons, we have pressure plates, or we just have torches. If I wanted continuous power, I could use a torch. The other thing to keep in mind is the input of one gate might be the output of another. And that's how you get the very complicated systems, where gates link into other gates, and you make them split and operate in different kinds of manners. So as I'm breaking my levers, as we move down the line, bear in mind that I have levers here for the simplicity of demonstration, but it could be anything, really. It could be levers, buttons, pressure plates, the start of another gate. It could be a torch if I wanted consistent power. There's a lot of different ways that we can generate an input. The important principle, though, is it a yes input or a no input? Is it on or off? The next gate we go down is what's called an AND gate, and then its opposite here is the NAND gate. Generally speaking, the gates will have the opposites will have an N in front of them. The AND gate is a useful little devil. The AND gate requires two of the same signal to change the output. Right now, I'm sending two off inputs with these default off levers. I can apply power to one lever, and it will turn this torch off. Or I can apply power to the other lever, but nothing happens on the end. I must have the same yes input from both in order to change the output to a yes. The reason this works, the reason it's called an AND gate really, is I must flip this lever and this lever in order to get a yes output. Or I must have power from this and from this. I must turn this and this on to get an on output. That's the way it works. The reason this works, the logic behind it, is as I apply power here, it will turn this torch off, but this torch is still off. My end goal with this gate is to turn this torch on and send power to this piston, or to whatever my output is. Once again, you don't have to have a piston as your output. The output could be another gate or door or pistons or any kind of contraption, really. And what did I just do? Oh, that doesn't need to be there. My end goal with this gate is to turn this torch back on and send power here. The only way to turn this torch on is to have both of these torches off. And the way you turn these torches off is by applying power to them with the lever. So if I only apply power to one, this torch is off, but this torch is still on. And this redstone still has power. Only when this piece of redstone is unpowered or gives a no output will this torch turn back on and we'll get a yes at the very end of the gate. So the only way to turn this, once again, the only way to turn this piece of redstone off is to not have power in either of these, and the only way to do that is to apply power to these, to apply power to both of the torches. The end result being that when I apply power here and here, I will get a yes output, I will get a powered output. If you've ever seen an adventure map where two people must stand on, or a co-op adventure map really, where two people must stand on different pressure plates in order to open a door, or in a single player where you have to stand on one pressure plate and put an object on another pressure plate in order to open the door, that is how they did it, is with an AND gate, and it's actually fairly simple. The opposite of the AND gate is the NAND gate, N-A-N-D. All of these are in capital letters. I-O, inverter isn't, but the I-O gate, or input-output, the AND gate is capital A, capital N, capital D, NAND, N-A-N-D, all caps. And the NAND gate is exactly the opposite of the AND gate, where I must have both switches flipped to on in order to get an off output. The reason it's different is there just isn't a torch back here. So as I turn it back to default, both of these torches are applying power to this redstone, which is just carrying the signal this way. And I just need to, once again, just turn this redstone off. If I only turn off one torch, the other torch is still powering that redstone. But if I turn both torches off, they're no longer powering this redstone. And the lack of power will retract the piston or give me the no output. So if you have an AND gate in your system and you discover that it's doing the opposite of what you want it to, like if it is closing your door when all of the power, or when you flip the switches properly, instead of opening it the way you want to, all you have to do is remove this torch and put redstone here instead, and you have a NAND gate, and it will just do the opposite. The next one down the line is an OR gate. It's very simple. I must flip one or the other or both to get the yes output. Yes or a yes or two yeses equals a yes. I'm going to go back real quick, and we're just going to address these in logic terms, in binary logic terms. So this gate, the logic is yes equals yes. That's very simple. This, the logic behind it is yes equals no, and that sounds really stupid, but that's the way the binary logic works. So in a normal I/O gate, yes equals yes. On an inverter, yes equals no. On an AND gate, yes plus yes equals yes. So only two yeses will equal a yes. This is also called an if and only if gate. I can get power if and only if both of these are pressed. So once again, this is a yes and yes equals yes. The NAND gate is a yes and a yes equals a no. When we go to the OR gate, the logic behind it is a yes or yes and yes equals yes. And it starts to get more complicated as we go down. There are more inputs and still only one output, so it sounds very complicated. But the basic principle is that I only need to flip one switch, and it doesn't matter which one. Whoopsie. Didn't mean to do that. I only have to flip one switch, and it doesn't matter which one. I can flip one or the other or both, and it will give me the yes output. The opposite of that is the NOR gate, N-O-R. The logic behind that is exactly the opposite of the OR gate, where a yes or a yes equals a no. And the reason these work, looking back at the redstone, is all I'm doing is taking power from two different objects and just linking it to the same output. So it doesn't matter which of these levers I flip, the whole system gets power. In this case, it's the exact same thing, except with an inverter in the system. So it doesn't really matter which switch I flip, it's sending power to the inverter, which will do the opposite and remove power from the piston. So in logic terms, again, that is a yes or a yes equals a no. The logic is important when you start to, if you wanted to build like ticker displays or large LED displays, the logic part becomes more important than the redstone part, because you have to logic through how the device should work. So if you're not sure why I'm giving you all these yeses and nos, it's because if you want to do something more complicated than just use a switch to open a door in some fashion or another, you have to understand the combinations of logic as you start linking gates. The next gate down is the XOR gate. The purpose of an XOR gate is such that I can't, as long as they are not the same, I'll have a yes output. So a yes and a no equals a yes, or a no and a yes equals a yes, but a no and a no equals a no, and a yes equals a no. So it doesn't matter which order I have them in, as long as they're not the same, will I get that yes output. The reason this works is, once again, I'm just taking power from these switches and applying them to what is very similar to an AND gate at the start. But as we'll go through this one, we'll start at the back and work our way towards the front. So right now, neither of these switches are flipped because everything is at default, so the default is unpowered. So neither of these torches are on. If I wanted to get a yes output, all I have to do is change one torch. So let's say I'm going to work on the left side. So if I change, the way to change this one torch is to depower this redstone. The way you depower this redstone is by removing power from this torch. The way you remove power from this torch is by applying power to it from the rear. So if I apply power, that will turn these torches off, which turns this redstone off. This torch turns back on, and it applies power to the piston, or gives me that yes output. Likewise, if I do the same thing on the opposite side, applies power, torch is off, redstone off, this torch is back on, power is applied to the piston. Let's say I have them both off. Power is not being applied to either of these torches. Excuse me. So, all of these torches are on, which means all of this redstone is on. Both of these torches are receiving power. This is no longer powered because both of these torches are off. And I have an off output, or a no output. Let's turn them both on and look at why is it still off if both switches are on. So with both switches on, both of these torches are unpowered. So this redstone is unpowered. These torches are unpowered. So the redstone here and here is receiving power from this torch and this torch alone. And from this torch, it's sending power to both of these pieces of redstone to turn both of these torches off and this redstone remains off. If I flip just one of those switches, it will flip this entire side. So this torch will turn off, but this torch will turn on and return power to or keep power off in this one, but the torch over here is no longer being held off by the central torch, so that this can actually turn back on. So the only way to make sure that I get that no output, or the only way to make sure I get a no, is all of these torches have to be off so that this torch can be on and both of this redstone can be powered. If any combination of these torches is on, this one will be off. And I'll get a yes output, is how this logic gate works. It's snowing again. I just turned snow off. What the crap? Anyway, this is an XOR gate. The logic behind it is a yes and a no equals a yes, or a no and a yes equals a yes, and vice versa. And a no plus no equals no, and a yes plus yes equals no. That's how that one works. The next one over is the XNOR gate, so that's exactly the opposite of the XOR. Stupid snow. Can't see anything. So the exact opposite is in place, where a yes and a no equals a no, or a no and a yes equals a no. But a no and a no equals a yes, and a yes equals a yes. So we'll walk through this again from the back. If you notice, the only difference here is... Where is the difference? Why can't I see it? The only difference is, of course, this inverter. So you've got your XOR gate. This is identical to the XOR gate, but we've just put an inverter right here at the end and flipped the signal. And that's, in a way, how all of the opposite gates work. If we go back to the AND and the NAND gate, this is just... The AND gate is a NAND gate with an inverter right here. And the NOR gate is an OR gate with an inverter right here. The XNOR is an XOR with an inverter right at the end. So the idea is just to get the opposite effect. XOR and XNOR are not very common gates. They're really only used in big devices. Not as much in adventure maps or traps or locks or things like that. I didn't mean to break that. Whoopsie. So we need a torch right here, and we need redstone right there, and that will fix it. Okay. So once again, if the XOR and the XNOR gates kind of bamboozle you, don't worry about it too much. You won't really need to worry about it unless you're doing really big redstone constructions at some point in the near future. The other gates that are really complicated that I'm probably not going to talk about are flip-flops. I might do a lab on flip-flops later. Flip-flops are incredibly complicated to build. The principle behind them is not terribly complicated, but to build them and understand them is kind of a pain in the butt. So I might devote a whole lab to them later. But once again, those are really only used in really complicated contraptions. And for basic everyday redstone purposes, all you need is input output through XNOR. I've thought about using some XNOR in some stuff on our server. I just haven't done a whole lot of redstone builds there yet. But in general, these are all you need. The last thing we're going to talk about, which is used in all kinds of stuff, is clocks, or are clocks, to be grammatically correct. And clocks have a million different, well, not a million different uses. I'm going to stop exaggerating. Clocks are useful in many different ways, in that they send an alternating pulse. It will pulse on and off, on and off, on and off. And that only makes sense if you look at, so this torch is in fact the output of the clock back there. We'll talk about how the clock works. But what the clock does is it will keep turning this torch on and off, or it turns this redstone on and off. And I can take this power to some device, so I can have a door constantly opening and closing, or a platform extending and retracting, or something along those lines. The most reliable and the most... I'm going to take that out of here. The most reliable and the original clock is this. This is called a 5 clock. I'm going to try and keep the snow off of it so it's easier to see what's going on. The way a 5 clock works is it's just a series of 5 inverters all in a row. So as the power reaches this torch, it turns off. So as this torch turns off, this one turns back on, and it keeps going around in a circle. So if you look at it, you can see the power kind of traveling around in a circle. And then all I have to do is find the wide opening in the 5 clock, because no matter how you build a 5 clock, there will always be one part of the 5 clock on one of the sides or on one of the corners that doesn't have a block there. It'll be the long stretch of redstone. That is your output area, and you just take power from there and wire it to whatever you're using. 5 clocks are the most reliable because they never turn off unless you break them. They will not break by logging out or turning the server off. And the only problem with a 5 clock is they're large. If you'll notice, this is kind of big, and there's no way to condense a 5 clock any smaller than this setup. This is 4 by 3, 6, 7 just for the clock, not including the output redstone. The other problem with the 5 clock like this traditional 5 clock, is it only operates at one speed. I can't make this clock go any slower. Well, I can make the clock go slower. I can expand the clock. I can turn it into a 7 clock. 7 meaning that there are 7... There's thunder. A 7 clock meaning that there are 7 inverters in the system. So I will go ahead and do that real quick just to demonstrate. Nope, not what I wanted. I keep trashing my lab surface. That's okay, I'll fix it later. And we'll apply redstone there, and we put a torch here and apply redstone here. So it makes a clock, and it works just like a 5 clock, except it's slightly slower. It has 2 extra ticks in there because there's 2 extra inverters. So with a traditional mechanical clock like this, mechanical being a kind of vague term, but with the old mechanical clocks, you can only go from a 5 clock to slower. There's what's called a rapid pulsar, which burns itself out. You can go down to like a 4 clock, but as you make these clocks any smaller than 5, or in anything that's not an odd number, they will burn themselves out, and they will not reliably tick like this. The only stable clocks are in odd numbers and anything 5 or larger. So the downsides of the 5 clock being they're big, or the 7 clock, or the 9 clock, or whatever it is. They're big, and I can only make them 5 ticks or slower. The way you get around that is, thanks to repeaters, we can actually use a completely different kind of clock. That is we'll get to that in a second. That's an RS-NOR latch. Oops, I messed it up. Let's see if I can get this right. The problem with these clocks is they're fidgety. They don't like to. You have to time them right to turn them on. There we go. Oh, damn it! You have to get the pulse working. You can trigger these with a button, but you have to have a certain timing on them to trigger them with a button. These are, if you can obviously see, they're much smaller. This is only a 2x4, not including what I had to use to trigger the clock. The other downside of this clock is previous to 1.1, they would turn off when you disconnect, or when you log out of in single player, or if the server turns off. My understanding of them is they are actually more reliable now. There was a patch in 1.0 or 1.1 that should fix that. Should be this map. Oh, no, they're still doing it. So yeah, as I log out, you'll notice that the clock turns just into constant power. Sometimes it will, when you log back on, it will go back to ticking. And the only times that happens is if you logged out at a point where there's only power in half the thing, or there's only in the thing, only power in half the clock. So if you log out at a very opportunistic moment, it can turn back on when you log back in. But if you're going to use a clock like this on a single player thing, on a server that will be turning off, or in an adventure map, you have to have a way to turn the clock back on. And the way you do that is by applying power in some kind of burst. The other benefit to this clock is if I can trigger it like I'm supposed to. The other benefit to this clock is it goes a lot, you can adjust the timing. It goes a lot faster, and it can go slower if you set it up right. Having trouble triggering my clock. Come on. Why aren't you triggering? When you get to the really low ticks, like there's no delay, or there's exactly, there's no delay in these repeaters right now, it's very hard to trigger the clock. So I have a thought. Let's do it this way. Alright. Why don't I just do it with a switch? That'd be easier, wouldn't it? Whoops. Alright. Apparently I'm not as fast as I think I am. That's annoying. I'm gonna have to ponder how to trigger this clock. I was able to do it before. Let's try it with we'll put a little bit of... Alright. I'm actually going to do it this way. See if I can get this stupid thing to fire. I did it before. Oh, still doing it wrong. This makes me look like an idiot. I feel dumb. Alright. There we go. Now we got it. I had to... Okay, let me go through how the clock works, and then I'll explain why I had to do that. So, this clock, the repeaters only send power forwards across the arrow. So as it's sending power this way, it goes around in a circle, and it'll just keep circling around, and with no delay in the repeaters, it goes really fast. So I can take this power and I can make a really fast opening and closing door, or a piston that will continue to fire very quickly with basically no delay. And there are mechanisms which apply this, like there are certain mechanisms which you'd want something to fire this quickly. Like if you wanted to operate multiple different speeds of a piston trap that's, trying to push someone off a ledge. Like if you wanted them to have to run really fast, the only problem is this is too fast, no one can run faster than this piston is firing. So you can get these clocks to go really fast, or you can take them and we'll make a really fast blinking light. Like so. The downside to using this for a blinking light is it actually blinks faster than the torch can update. So it's going to keep burning out. And you can actually use this as a kind of AI thing, or a random generator. So you get this torch will burn out at random intervals. So you can use that to randomize certain things. The way you'd actually set that up, if I wanted to set up a random thing, is use multiple torches, and whichever one burns out first will trigger a certain result. And you can use that for random number generators or randomization of basically anything. The benefit to this kind of clock is it can go really fast like this, but I can also slow it down. I'll put in another tick delay there, and it'll actually fix itself now that it's a little bit slower. So as you notice, this actually is firing a lot slower than that other clock. Or if I add another tick in there, it's now firing even slower. Or I can add another tick, and it now fires even slower than that. And I can continue to make it go even slower by extending this clock out, putting more repeaters in, and just adding another tick delay on each repeater. I don't know why my brain failed there. You do not want to put in a different delay on the two repeaters unless you want a really wonky clock. What this will do is the clock, if I do it right, is it won't be stable. It will not want to remain on. So if it won't, like, this one won't even turn on because the difference in delay is too much. I'm going to try that. Nope, didn't do it fast enough. Yeah, they don't want to stay on because the difference in delay means that at some point the redstone circling around will overlap itself and the whole system will be on. And for a clock, you want it to keep alternating. So the only way to keep it alternating is to make the delays the same. See, now we've got it working. Now, the reason I had to put this inverter here in order to make my clock work like it's supposed to is without anything in the way, redstone power transmission is instant. If you watch me flip this torch, the transmission is instant. If I add, or flip this lever, not torch, the transmission is an instant transmission of power between this redstone. If I add a torch, it adds a very slight delay. And it's very difficult to see. I'm going to try an angle. There's about a half a tick delay for every torch in the system. Or when it's actually about a whole tick, which is why the 5 clock system works. So I had to add a delay in my application of the power, so that there was actually a very slight pulse to the way I applied power to this clock system. Because if I just applied constant power with this lever, I have to flip it really fast. Otherwise, it'll just be constant power and the whole thing will be on and it won't clock like it's supposed to. So this clock system, again, it's smaller than the 5 clock. You can adjust the rate at which it fires. And the fact that I have to turn it on or off is both a blessing and a curse. If I want something to be constantly firing all the time, when I'm near it, it's firing. When I'm not near it, it's firing. You want a 5 clock. Because 5 clocks will never stop firing. It will always be on. The fact that this clock isn't on until you turn it on, and it will turn itself off. I was just weirded out by the gray block there. This clock will turn itself off when you log out of your single player or disconnect from the server, is in a way beneficial for adventure maps only. So that you can have a player, when they enter a certain room, you set it up so that they press a button to start the clock firing. And the button presses, it sends a pulse, the clock starts firing, and then at some point, when they get to the end of the puzzle, you can have them flip a lever and turn the clock off so that your redstone contraption doesn't keep, spamming doors or spamming pistons while they're away from it and causing lag on the map. So there are benefits and downsides to this, and it really depends on your application. I try and use these as much as possible, for one, because they're smaller, and for two, because I can make them fire faster. The last thing I'm going to talk about in this lab is, in a sense, it's a logic gate. It's called a RS NOR latch. RS NOR latches have several different uses, but their main one is based around the fact that they're called what is called a binary memory latch, or a single cell memory cell. And the reason they're called that is they remember what the input is. Remember in quote marks. It's a machine. It doesn't actually have memory. Well, memory in the sense that computers have memory. But if there are exactly 2 inputs and 2 outputs to this device, and as I actually apply power to this side, it will turn power off on the other side. So I can flip the power back and forth, and I don't necessarily have to do it with a button. The reason this becomes useful is, whoops, I didn't want to do that. Let's say I apply power here. I've now flipped this system on. And then I remove the power, it stays on. So I can take some kind of device that works on timing and buttons and only sends a pulse. And if they get that pulse timed right, it will open the door and the door will stay open. It's very snowy. Holy crap. And XNOR latches, the fact that they remember which side you flipped last, is applied in large redstone contraptions where you remember what was on last and you take whatever was on last and do the opposite. So it is called a single bit memory cell, or a single cell memory unit. What most people refer to it as, like if you've ever seen Captain Sparkles, or if you've ever seen anybody else that does redstone, they'll just call it an XNOR latch, because that's its logic gate name. But this has a lot of different uses, and you'll see these used in kind of weird different applications. Like when we get to the lab for the button combination lock, you'll see these daisy chained to trigger the combination. If we ever do any LED or ticker displays, you'll see these used as memory cells to know which LEDs to turn on or turn off when they get a certain input. And these are fairly common. These are used all the time. And the way these work is, once I've applied power to, say, this side, so once I've applied power here, it removes power from this torch, and this torch can be turned back on. Once I apply power on this side, it's applying power to this torch, so the torch turns off, and then this turns off. So there's no longer power to this torch. This torch is still on, and it's still applying power to this torch. So whichever one I have turned on will stay on until I apply the opposite input. If any of this is incredibly confusing, I'm sorry. I tried to make it as simple as possible. If you have questions, you can, of course, comment, or you can send me an email. I will put my email in the description. I'm more than happy to try and help you with your redstone conundrums. And as you move forward, hopefully you can take what I've taught you here and apply them to your own devices. Future labs will, of course, include more redstone devices that I'll build step by step so you can copy me, but my hope is that it will stop snowing in my lab. But more than that, my hope is that you'll be able to kind of work on your own with what I've given you. And with that, I will end the episode. Hopefully you learned something. Hopefully this was a little bit more... This was easier to understand than a lot of other redstone labs out there, or redstone tutorials. And likes and rates are appreciated. I will catch you next time.